Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 4, Distance Vector Routing. And before we take a look at the overview that I've put here on the board for us, I want to give you a word of warning. When it comes to distance vector routing, I mentioned this when we talked about static routing in a previous video. For those of you who are CCNAs already, and especially if you've recently completed it, you may look at this list and say, well, I already know this stuff. I really don't need to watch this video. Let's go ahead and get to BGP or multi-area OSPF. Do not make that mistake. We're going to look at a couple of facts here when we discuss distance vector routing that are not part of the CCNA curriculum, but they are part of the BSCI curriculum, and they're also things you need to know to be effective with these in the real world, on your current job or on a future job. Because it's not just about being certified, it's about knowing what you're talking about and being able to defend a position. And the first one that we're going to look at, the first position you may need to defend, is when to use distance vector routing and when not to. Because your boss may say, I want to run RIP version 1 over a WAN because it's a simple protocol, and that way we don't have to have anybody in here who's really good. So you want to be able to defend that position and defend your job and say, well, maybe that's not a good idea, and here's why. After that, we're going to take a look at some basic distance vector protocol behaviors, and those are designed to prevent routing loops. We can see some of those in action. We don't see others in action, so we'll discuss them here. We're going to look at the basics of RIP, IGRP, and EIGRP. You're going to see very little IGRP on your BSCI exam, if any. And you're going to learn quite a bit more about EIGRP in a later video in this course, because what you learned in the CCNA as far as EIGRP goes is just scratching the surface. And we're going to take a look at that later, but right now in this lesson we're going to do a basic comparison of the three. We're also going to revisit administrative distance. We talked in an earlier video about how the routing table operates, when administrative distance comes in and when it doesn't come in. We're going to review some common AD values that you need to know for the exam. Then we're going to look at something that's probably brand new for most of you. This is RIP version 2 Update Authentication. RIP version 2 allows us to configure authentication for the routing update packets themselves. And that is some tricky syntax. I will warn you ahead of time. So we're actually going to do that twice. We're going to look at it on the whiteboard first, and then we're going to look at it as part of a case study. And the case study is nothing fancy, but it's going to tie in everything we've talked about here in this course, here in this video, about distance vector routing, and particularly with RIP, because this exam is a little heavier on RIP OSPF comparisons than anything you did before. And I do include the EIGRP basics here. I know that officially that is not a distance vector protocol, it is a hybrid protocol, but you need to be ready to compare some of the basics to RIP and to IGRP. So getting started with that, let's take a look then, first off, about when we're going to use distance vector routing and when we're not. And of course the reasons why. If your boss says, why don't you want to run RIP version 1 or RIP version 2 over the wide area network, you have to be able to tell them why, not just that you saw it somewhere. And the big reason is right there in front of us, that first note that I put up here under the update timers, is that a full routing table is sent out every 30 seconds with RIP and every 90 seconds with IGRP. And just to verify that, I'm going to bring up the rack here. I have RIP running on router 1 and IGRP running on router 2. And we always come back to show IP protocols. We're going to be doing this a lot in the upcoming courses, in the upcoming videos. And what we see here is that when we're running RIP, the updates are sent out every 30 seconds. In a stable network, which is the kind we're always hoping to get, that's a lot of updates. Now, over here on router 2, where I set up IGRP and RIP, you recall, of course, that the routing protocol number there is the AS number, the autonomous system number. And the updates go out every 90 seconds. This is a little better, but still in a stable network, That's a lot of updates. It's a lot of work on your router because the router's got to look at every single one of those updates. And if we're sending this over a WAN, we're taking up just a little bit of bandwidth for our wide area network that we don't need to be taking up. And you see the hold down timers there for IGRP as well. So those are really the two timers. Those are the major reasons why we do not really see distance vector protocols used over wide area networks. They take up a little bit of bandwidth that's better served in using for other purposes. And we really want a routing protocol that's only going to take up bandwidth on the wide area network when it's needed. That is, when there is a change in the network topology. And RIP and IGRP don't work that way. Now another reason, and this is a bit of a surprise to a lot of people, RIP routing updates can only contain 25 routes. Now you've run debug IP RIP before, and we'll certainly run it again before the end of this video several times, because debug IP RIP actually allows you to see the contents of the routing update. But if you've got 30 routes, say, it's actually going to take 2 separate RIP packets to carry all those routes. That's a really good detail to keep in mind. If you've got 110 updates, 110 routes, it takes 5 packets to advertise all those routes, because 4 of them will be full at 25 and then you have 10 left over. So keep that one in mind, and that's another reason why, since your wide area network tends to carry a lot of routes, that not only will RIP send an update every 30 seconds, it may be sending multiple packets every 30 seconds. RIP version 1 and IGRP are classful routing protocols. There's no VLSM support, no subnet masking support whatsoever. And that's not real good either, especially for our wide area network. We can probably live with that on a small LAN. But when it comes to the WAN, we're not going to want to do that. And the big one here, especially with RIP, we know that IGRP uses a composite metric that still has its limits. But the big one for us right now is that RIP only understands hop count. So in a scenario like this, between router 1 and router 2, there are 2 paths, and obviously one is much faster than the other. The path going through the top router is connected to 2 T1 segments, and on the bottom, 2 56K segments. The problem with RIP here is that RIP only understands hop count. So RIP would look at this and say, okay, the hop count is the same for both paths. I'm going through the same number of routers. That's not very sophisticated routing, I think you'll agree with me, and it's not what we need on our wide area network. Because then RIP, of course, since it is enabled with equal cost load balancing by default, it's going to load share by default over these 2 paths. And when you're load sharing over a T1 and a 56K connection, that's not a good idea. Not what we want to do. Now, IGRP and EIGRP don't use that hop count metric. They have a more complex method of calculating the best route. And just to make a note, as I'm sure you recall, EIGRP actually uses the dual algorithm, the diffusing update algorithm, to calculate the best route. But those 2 protocols may still have a problem with this because of the assumption that a serial interface is connected to a T1 line. So while IGRP and EIGRP don't quite have the limitations on the metric that RIP does, the problem is that you may have to do a little tweaking with the bandwidth command with IGRP and EIGRP. So just keep in mind, they assume that any serial interface is connected to a T1 line. And we fix that, or we adjust that with the bandwidth command. That doesn't actually change the bandwidth. I'm sorry, it's not that simple, but it changes IGRP's and EIGRP's assumption about these lines. We could put 56 bandwidth 56 on router 1 and router 2's interfaces here, and then all the traffic would go over the T1 line. EIGRP is perfectly suitable for a wide area network, since it does have VLSM support, but IGRP and RIP, either version, are not. So we're just going to revisit a couple of old friends here, our distance vector protocol behaviors. And the reason we have these behaviors is to prevent routing loops in the first place. And in this scenario, we're looking at split horizon. And split horizon states that a router cannot advertise a route out the same interface upon which it was originally learned in the first place. And in this simple example here, we've got router 1 advertising the network 12.0.0.0 out an Ethernet interface. And it goes down to R2, the update goes up to R2, R2 puts it in the routing table, we'll just say via R1. And if we're running a distance vector protocol here, R2 is going to want to advertise all the RIP routes or IGRP routes that it had learned, but it's not going to be able to advertise that route back out the same interface that it learned about it in the first place. And that is split horizon. That is a default behavior. It cannot advertise 12.0.0.0 back out the same interface. This is a default behavior of distance vector protocols, and it can be turned off at the interface level. We may just see that situation later where to get a complete routing table for our network, we may have to turn split horizon off, because every once in a while it's going to interfere with your routing. It's not something you want to just turn off every time. It's not like auto summarization where we turn that off almost every single time with RIP version 2 and EIGRP. So another protocol behavior, distance vector protocol behavior that is poison reverse. Now, poison reverse allows a router to advertise a route with an unreachable metric when the route becomes unavailable. Now, I definitely remember reading that when I started studying for the CCNA, and I thought, well, what else would it do? I mean, shouldn't it, what I used to think should happen here is, why doesn't it just stop advertising the route? Why does it have to advertise it as unreachable? Why doesn't it just stop? The reason it doesn't stop is because distance vector protocols converge very slowly. And convergence is simply the process of all your routers in a network agreeing on a network change, and they've all caught up with that change. This is another reason you don't see distance vector protocols used over WANs very often, is that the convergence is very, very slow. So what I'm going to show you here, and I want to reiterate this, this is what would happen if poison reverse did not exist, because you may think, as I did, well, why doesn't it just stop advertising it? There is a reason. Let's take a quick look at why here. In this scenario, and let's just say we're running RIP over the entire network here, this is a little different than the network we're using in our pod. Note that router 2 and router 3 do have a dedicated path between each other. So in this scenario, router 3 is connected to network 3.0.0.0, and since we're running RIP, it's going to advertise it to both router 1 and router 2. And let me get rid of the red there just a moment. Thank you. And it's going to say, hey, I'm connected to 3.0.0.0. It's one hop away. It's going to advertise the same thing to router 2. Now, of course, router 1 and router 2 cannot advertise that network back to router 3 because of split horizon. But either router 1 or router 2 is going to advertise it to the other. And in this scenario, we'll just say router 2 is advertising to router 1. Hey, I've got a route to this network, and it's 2 hops. And we want this. This is redundancy. We want this. Because what will happen is router 1 will get both of these updates, and it will install the more direct path, the one hop path, into its routing table. And it will see the update coming from router 2, and it will see that it's got a higher metric, and then just discard that particular update. But we want this, it's redundancy. So if that direct link between 1 and 3 goes down, then router 1 still has a path to that network. So this is what would happen if poison reverse did not exist. And you may have already spotted what the problem would be. Something terrible happens to this connected interface, to this network. And now, what I used to think would happen, and what a lot of people still think would happen, is that router 3 would just stop advertising it. Excuse me. So if it stops advertising it, it's not going to send it to router 2. So we'll just take those arrow points off. It's going to stop advertising it to router 1. And now we have a little problem though, because router 2 is going to continue advertising it to router 1 because of the slow convergence of distance vector protocols. If we run show IP protocols again on router 2, we can get a reminder that it takes a long time for a route to actually come out of the table. We got to go through the invalid timer, the hold down timer, and then finally the flush timer. That's a long time. I've seen routes just in practice labs, like the one we're using, take a long time to come out, because you know what you get? You get a message that says the route is possibly down. And that's not what we want. We want the route to either be up or down. But this is what would happen if poison reverse didn't exist. Then it gets worse, because router 1 would then advertise the network back to R3, because split horizon would no longer be in effect. And say, hey, I got a route to that network. And now you've got a disaster, because then router 3 is going to advertise that to router 2. And router 2 is going to keep getting it and say, okay, let me advertise that to router 1. Now the hop count will continue to increment. And what we've got there is a maximum hop count of 16 with RIP. When a RIP route hits a hop count of 16, it's considered invalid. But you can see how long that's going to take for it to even get that high. And meanwhile, you've got just a routing loop from heck. And anything that anyone is trying to send to network 3, it's just going to go in that loop, 321, 321, 321. And all the time, the network is down, the data has no chance to get there. So this is why poison reverse exists. That's what would happen if we didn't have it. So, now that we do have it, what exactly is going to happen? What is going to happen here is that router 3 sees that that route is down, unavailable, and sends out an advertisement for it, but marks it as unreachable. That's what actually happens. So now, when router 2 gets that update, it will remove the route from its routing table. And router 3 will do the same with router 1. This also prevents router 3 getting sent any rogue routes for that network from 1 or 2. Because router 3 is telling them, hey, it's unreachable. And what will happen is router 2 will then stop advertising it, because it's going to be removed from its routing table to begin with. So that's why poison reverse exists. That's what it does. And I hope that cleared up. If you weren't quite sure why poison reverse existed, I think that'll clear it up for you. Because it's one of those things where you can memorize it real easy for an exam, but then you think, well, what would happen if it didn't do that? Well, we saw what would happen. This is a default behavior of distance vector protocols, and it cannot be turned off. You can't go to a router and type no IP poison reverse. Doesn't work that way. Because getting rid of this can really lead to routing loops very quickly. So split horizon and poison reverse are two of the mechanisms that distance vector protocols use to fight routing loops. And just to mention another one that we saw in action here, there is the problem of counting to infinity. Counting to infinity simply refers to the fact that if we have a routing loop form, as we saw here somehow, what happens is the route would just continue to increment, the metric would continue to increment, but it would still be advertised. You know, what happens when it gets to 200 hops? What happens when it gets to 250 hops? Well, nothing unless we have a maximum hop count. The maximum hop count fights the counting to infinity issue. And you already know that with RIP, that maximum hop count is 16. It's 15 for a valid route. Now you will see, it's not something you're going to see on your exam, but you'll occasionally see on the net there's a real argument about what the maximum hop count for IGRP is. But if you know where to look for it, there is no argument. It's right there. It's 100. Sometimes Cisco documentation will contradict itself. You've probably already run into some of that in your studies. If you haven't, you will. But always come back to the router and just run the right command and see what the value is. So the maximum hop count for IGRP is 100, but again, I haven't seen too many of those. And you'll notice for RIP, it does not list what it is. So you got to know that. So we've looked at split horizon. We've looked at poison reverse, and we have looked at the maximum hop count problem solved with counting to infinity. Now let's take a look. Next board. We're going to look at that here shortly, but right now we're going to go over a RIP version 1, RIP version 2, IGRP, EIGRP comparison. Just some reminders of some facts you learned when you, mostly the facts you learned when you studied your CCNA. There may be a little new information in here. RIP version 1, again, it broadcasts its updates. We know what a layer 3 broadcast looks like. Every 30 seconds, whether there's been a change in the network or not. RIP version 1 is classful. There is no VLSM support. The other thing that you got to watch with distance vector protocols is that the update packet contains the entire routing table. And I'm going to say RIP table there because sometimes people get a little confused. It's going to have all the RIP routes. It's not going to have all the connected routes or anything like that. We've got the algorithm, and RIP actually uses an algorithm. You wouldn't think it would need an algorithm, but it does. It uses the Bellman-Ford algorithm. It does have equal cost load balancing by default. And that's over 4 paths. It does not support routing update authentication. And again, just as a reminder, since this is the big new fact here, the updates carry 25 routes maximum. So if you're ever asked, just say, you know, hey, we got a little thing here where RIP is advertising 110 routes. How many packets do we need? We need 5. Because 4 of them will be full up at 25 and the other will be carrying 10. Now, we're going to look just at the differences here between RIP version 1 and RIP version 2. And the first one is that RIP version 2 does multicast its updates to 224.009. RIP version 2 is classless and does support variable length subnet masking. It uses the Bellman-Ford algorithm. Its updates do contain the entire RIP routing table. It does have equal cost load balancing by default, so those 3 things are similar. It does support routing update authentication, as you'll see soon. And again, the updates do carry 25 routes maximum. So the 3 things that I've put down there under RIP version 2, those are the big differences from RIP version 1. And when it comes to IGRP, as in the real world, I don't expect you to see a lot of IGRP on your exam. But just the basics here. It does broadcast updates, but every 90 seconds. IGRP along with EIGRP are Cisco proprietary protocols. Try to say that 5 times real fast. It is a Cisco proprietary protocol, so if we're looking at a multi-vendor situation, it is not suitable for that. It is a classful protocol and does not support VLSM. IGRP also has an algorithm. It does use the Bellman-Ford algorithm. Equal cost load balancing is on by default. And of course, we can use the variance command for unequal cost load balancing. The maximum hop count, as we looked at, is 100. With EIGRP, just looking at the differences here, EIGRP does multicast its updates. Remember the address? 224.0.0 is the easy part, right? 10. 224.0.0.10. It does not send them out on a regular basis. It sends updates upon an adjacency forming with a neighbor and when the network changes. But that's it. It's not going to send something every 30 seconds or every 90 seconds. It does allow VLSM. It is a classless protocol. EIGRP uses the dual algorithm. It does have equal cost load balancing on by default, and the variance command again is used for equal cost load balancing. While we've got these 4 up here, actually let's bring up another screen for that. Quick review of administrative distance. It is the measurement of a protocol's believability. We talked in an earlier video about how the router decides between what the best path is between paths that look just about the same. You recall it looks at the longest prefix length first. That's the longest match rule. If the matches are exactly the same as far as the prefix goes, something like this. In that case, now administrative distance has to come in because the prefix length is exactly the same, but we have 2 different, it would actually be the next hop, but I just put the local interface. So the router's got to decide now which path to choose. And this is not something we see happen on the router, but for exam questions and to be able to troubleshoot routing problems on our network, we've got to know the administrative distance values right off the top of our head. Now the directly connected route and the static route using the exit interface is 0. That's a good detail to keep in mind because we recall from an earlier video that when we created a static route using the local exit interface in the IP route command, it appeared in the routing table as a directly connected route. It still had S next to it, but then where it would usually in the middle of the line, it said directly connected. So that's why it's got an AD of 0. And a static route with a next hop IP address in the command has an AD of 1. A couple of EIGRP routes you may not be familiar with, but you will be by the end of this course. EIGRP summary has an AD of 5. A couple of these you haven't looked at yet, but I'm going to list them here anyway. External BGP is 20. Now I'm going to put internal EIGRP at 90. That differentiates a little bit from what you learn in your CCNA studies, because with EIGRP you're just told, well, the AD is 90. Well, I've already put one different EIGRP AD up there, and I'm going to put another one up in just a moment. because again, in your CCNA, you barely touch on EIGRP. We're going to look at these more in depth later, but I want to introduce you to this now, that not every EIGRP route has an AD of 90. It's a little misleading what they teach in the CCNA. So we've got internal EIGRP at 90. We've got IGRP at 100. These are the more familiar ones. OSPF's got an AD of 110. RIP's got an AD of 120. External EIGRP routes have an AD of 170. Just to throw this at you now, all we mean by external is it was learned by redistribution. And then finally, we're going to put one more up here you may not be familiar with yet, but you will be. Internal BGP has an AD of 200. So when we're talking external, internal here with a couple of these, internal means it's a native route. This protocol discovered, and an internal EIGRP route was discovered by EIGRP without any help. An external route is one that is learned via redistribution. So we've taken a look at that. We've taken a look at the comparisons here. We talked about routing update packet authentication. And this is an advantage of RIP version 2 over RIP version 1, is that we are allowed to configure a password for the routing updates themselves. Now we've got two choices here: clear text and MD5. Now clear text is just what the recipe says. The name is the recipe. It's clear text. When we run a debug later on a clear text authentication, you're going to clearly, no pun intended, be able to see what the password is. Now, as you're going to see, this is not the hardest thing you're ever going to configure, but the syntax is a little tricky till you get used to it. If I'm going to the trouble of configuring RIP version 2 authentication, I'm going to use MD5. Now, MD5, the MD stands for Message Digest, and that's the algorithm that is going to produce the hash value for the password that will be contained in the updates. So if you do a debug there, you're just going to see a string. It's not going to mean anything to you. But anybody that knows how to run debug IP RIP is going to be able to see what your password is. Now, a couple of notes about this before we do it live here shortly is that first, each router interface on a link or segment must agree not only on authentication. It's not going to fit. There we go. On authentication, but the type of authentication. So what actually happens is, if we configure router 2 and router 3 to use RIP authentication on that Ethernet segment that they're connected to here, not only must they both agree that we're going to run authentication, they have to agree on the type of authentication used. If one router is trying to use clear text and the other is trying to use MD5, even if the password matches, that's not going to work. It's going to blow up immediately. And what we end up doing here, I'm going to put it on the whiteboard, and we're going to see this in action in a couple of different fashions very shortly. What you do first is you create what we call a keychain. And a keychain has a key, and then it's got a key string, which is actually the password itself. It's going to look something like this when we configure it. We'll just call it keychain RIP. We can set different numbered keys on it all we want to. And then finally, the key string is going to be the password itself. So we have to create keychains, and as you progress through your Cisco studies, as you take some security courses, as you get some security certifications, which are going to be more and more important as time goes on, and especially as you climb the mountain toward the CCIE, you're going to be writing all kinds of keychains. We've got a lot of different options here. But the ones that we need to know for the BSCI exam, and the one you need to learn to begin with, is just the basic one. Then we apply it to an interface. We don't configure it under the router RIP command. So we've got two commands to apply this one on an Ethernet interface. The first one is simply naming the mode that we are going to use. IGRP Authentication Mode MD5. If we want to use clear text there, we just type clear. That's not the only command though. Now you've got to name the keychain. And that's how we're going to apply it. We're going to create the keychain first, and then we're going to apply it to the interface with two commands, first naming what the mode is, and then naming what the keychain is. One note before we do head for the lab is that this is case sensitive. And what I'd like to mention here, as you go through your Cisco studies, and you take security courses, you look at some voice stuff, you keep climbing the ladder, you go for the CCIE, you'll continually see posts on the internet where people are asking, is Command X case sensitive? And the problem is that some of them are and some of them aren't. If you choose one syntax to stick with today and always use, I should say the case, not the syntax, if you use one case, either upper or lower, whichever one you're comfortable with, and you use that for every password and every command for the rest of your career and the rest of your studies, you never have to worry about whether such and such is case sensitive. You never have to worry about it because you're using the same case all the time. I see people at the CCNA and the CCNP studies get in the habit of switching case. You know, they'll do lowercase for some commands for passwords and then uppercase for others. Don't do that. You want to develop your good habits now, and one of the best habits you could ever develop, and I have seen engineers sweat for an hour over something, and it ended up being the case that they put a command in. Choose a case now, either uppercase or lowercase, and stick with it for the rest of your studies. It shouldn't surprise you also, to bring the router up for just a moment, that if we want to see if authentication is being used, it's our friend Show IP Protocols. And it's going to be right here under Keychain. It's going to say something there about what the name of the keychain is. And if you see that, you know that you're using RIP authentication. Now, knowing the theory is fantastic. That's what we want. You've got to understand the theory before we see it in operation. But now we're going to see all of this in operation on our network. I've made a couple of changes here to begin this next lab. We're going to run a RIP domain, but at first we're just going to run it over the frame. Routers 1, 2, and 3 are communicating through the frame. Router 1 is the hub. There is no direct link right now between 2 and 3. Anything that those two routers send each other has got to go through router 1. Each router is going to be advertising its loopback. Remember, it's the loopback interface for each router is the router number 4 times with a 32-bit mask. So that's what we're going to start out with RIP. And let's bring our pod up here. And any time that I get ready to configure a protocol, whether it's in a production network or my home lab, I always run Show IP Protocols first. Especially in a home lab, you may not have gotten rid of the last configurations you wrote, and you've written this RIP thing, and all of a sudden you're like, where are these IGRP routes coming from? And you left IGRP running on there. So just as good form, whether it's at home, whether it's on a rack rental, whether it's in a production network, before you start configuring a protocol, always run Show IP Protocols to make sure that something isn't running that shouldn't be running. So we're going to start our RIP domain here simply with the command router RIP. We're going to use two network commands to advertise via the frame and the loopback. I'm going to do the same on 2. Run a RIP. Network 1000 should be 2 here. And the same commands here over the frame. And that'll be network 3. Let's go up to router 1 and see if we already see any RIP routes. And again, there's nothing wrong here with running show IP route. It's just a little easier and a better habit to get into. If you want to see just your RIP discovered routes, just run show IP route RIP. So we already see the two addresses, the two networks that the remote loopbacks are on. Now, 172.12.123.0, the frame that's connecting to 3 is not showing as a RIP route because it's a directly connected route. And that's a good thing to keep in mind for the exam, because it really shows you understand what's going on. If I show you this drawing and the whole thing is a RIP domain, and on router I ask you, what RIP routes should I expect to see on router 1? Well, I should expect to see the remote loopbacks as RIP routes, and we do, but I shouldn't expect to see the frame network as a RIP route because it is a directly connected route. That's something really easy to get wrong when you get asked that. Let's see, 172.12.123.0 is directly connected. RIP didn't have to discover it. Another thing to note here about the RIP routes is that while these loopbacks are all configured with 32-bit masks, they're showing in the routing table as having 8-bit masks, because RIP by default has a strange setup as far as what version it's using. You're very familiar, of course, with version 1 and version 2, but RIP does not run in version 1 by default, and it doesn't run in version 2 by default. We go back to show IP protocols, as we always do, to see what the default is. And the default is that it is sending RIP version 1 updates, but it will accept versions 1 and 2. So right now, since we didn't do any hard coding as far as the version goes, then we've got a situation where everybody is sending type 1 updates, version 1 updates, but it will accept 1 and 2. That's why we're not seeing the subnet mask information that we might expect to see. We're going to change that in a minute, and you'll get a first-hand view at even on a small home lab like the one we've got here. RIP takes a while to converge on network changes. So we've got that set up so far, and we'll do another look at the RIP routing table. And one thing you always want to get in the habit of in a production network and the real world is testing your basic IP connectivity at the very beginning. Do not make the assumption that just because you see a route in your routing table that you have IP connectivity to it. That's not the same thing. You can have a route to a remote destination and not be able to ping it. It happens all the time. It happens more often than we would like, because you could have a downstream router that has a problem with the route. So here we're fine. So just to check things, we'll go over to router 2 and do a show IP route RIP. And we see the advertisement for network 1, but not for 3. Okay. Well, we will ping router 1's loopback, and we get 5 exclamation points. That's what we expect to see. Do you think it's odd that we're not seeing router 3's loopback? Should we be expecting that? Let's clear the routing table. Never hurts to clear your routing table in a home lab, that is. And let's take a look now at show IP route RIP. And we're still just seeing router 1's loopback. We have connectivity to it. Let's take a look at our network. This is what we've got enabled with RIP right now. Let's try pinging router 3's serial interface from 2, the one that leads into the frame. Make sure that we have that connectivity. And we do. Think there's something odd going on, or maybe something not so odd's going on. Let's go over to router 3, take a look at show IP route RIP. We're only seeing router 1's loopback, and we can ping it, let's try pinging router 2's serial interface, 172.12.123.2. No problem there. What do you think? What do you think? What is the problem here? You can pause the video here for a second and try to figure that out. See if was there a configuration problem. You watched me configure it. I don't think there was. I put the frame network and the loopback interface on each router into RIP. So we shouldn't be having a problem with that. You know, anytime that we're not seeing the routes we think we should see in RIP, we should always run debug IP RIP. We're going to go ahead and clear the routing table so we don't have to wait for the next update. So we'll clear that, and we should see some updates come in, yeah. And we're going to go ahead and just stop it right here with undebug all. Because we've already got the information I think that we're going to need. Let's see, we sent the request. You see that we are sending version 1. And here are the broadcast requests on the local interfaces. Received a version 1 update, so we're definitely getting the version 1 update, but there's only one route in it. There's only one route in it, and that's the route to 1's loopback. It's kind of odd. Let's go to the hub, see if we can see what the problem is there. We're going to debug IP RIP, clear the routing table of its dynamic routes, and we should see quite a bit of activity here. Actually, we've already seen what we need to see, I think, because we sent out a request, a broadcast request, for the updates. And we see that router 1 is getting the routes to the loopbacks 2 and 1, 2 and 3, I should say. So that's kind of odd. Let's take a look at that RIP routing table again. And there we are. So it seems like the problem is that RIP version 1 isn't advertising router 2's loopback to 3. It's going up here but not back out. Router 3 is advertising its loopback up to router 1 and not back out. What is that? That is split horizon in action. And this is the kind of scenario where split horizon can get in the way a little bit. Because we can't have a full routing table because the update for router 2's loopback enters serial 0 on router 1. And by rule, it cannot be advertised right back out to router 3 because router 1's using the same interface, serial 0, to communicate with router 2 and router 3. That's why we don't have the total IP connectivity we might otherwise expect. On router 1, let's run show IP interface. Can we put serial 0 on the end of that? Yeah, we can. We get all kinds of information here about interfaces. And what we're looking at right here is that split horizon is enabled. This is a great command, show IP interface. Great command. So we got a problem there. What we can do, and you should be careful about doing this in the real world, but what we can do here is on that interface, we can turn split horizon off. And the command is no IP split horizon. No IP split will do the job. And if we needed to turn split horizon back on, we'd simply put in IP split horizon. So let's run show IP interface serial 0 again. And now we see that split horizon is disabled. And let's see what that does for our routing tables on 2 and 3. Let's see if they've already caught up. Go down to router 2, show IP route RIP. Yeah, they've already caught up. See, now that we turn split horizon off, router 1 is now allowed to advertise a route out the same interface it learned it on in the first place. And now we'll have connectivity. Yep. It's just that simple. But you see what we did when we had a problem. We tested our basic IP connectivity before we got too fancy and started adding a lot of other stuff on. And as soon as we saw a problem when the pings didn't go through, we ran a debug to see what was going on with the routing advertisements. Now granted, this is the kind of thing where you may have noticed this right away when we started this. You might have said immediately, well, split horizon's going to be there, it's going to be a problem. but that's where we separate the real network administrators from the wannabes, is with debug commands, because we know now exactly what is going on. So let's go back up to router 3. We'll hop over to 1 and run show IP protocols and see what's changed, if anything, here. And we see the updates are being sent every 30 seconds like we expect. We already took a look at the version default. Automatic network summarization is in effect because we are sending version 1 updates. There's the maximum path value, default to 4. There are the routes that we're routing that are RIP enabled. And here are the routers that we're getting information from in the first place. So what we're going to do right now then is hard code this entire network for version 2 updates. But we're going to do router 1 first, and it's a very simple command. It's simply version 2. And what this does is it's going to set every interface on the router to send and accept only version 2 updates. The other command I like to use here, right after version 2, and it doesn't hurt to run it again, I always put no auto summary to turn off auto summarization. So I'm going to clear the routing table, let RIP catch up with itself while we take another look at show IP protocols. And as you can see, you always want to verify your changes. Now the default is send and receive version 2. And you can see that now on the interface as well. You can also see that automatic network summarization is not in effect. We turned it off. So let's see what our routing table looks like now with show IP route RIP. That's not good. It's empty. It's empty. Let's see if we have any kind of problems we need to know about on the other side here. Oh boy, see, this is where distance vector protocols get a little confused, because now you've got 2 routes here where you probably don't want 2 routes, even though they've got the same next hop. One has the subnet mask information, one doesn't. So let's clear the routing table and do a show IP route RIP. And we've got 1 so far. Let's see if we still have connectivity to 1. Yeah, we've got it. But we lost router 3's loopback again, didn't we? Let's run a debug IP RIP. Clear the routing table. And wait for the packets to come in. There are the requests being sent out. Building some updates. Got a version 2 update. Let's go ahead and turn it off there. This could be our problem because it's sending version 1 updates. That's the default. Router 2 is sending version 1 updates, but we hard-coded router 1 to only accept version 2. So that could be a problem right there. And you'll see here, received a version 2 update with only router 1 in it. That's because right now, routers 2 and 3 are sending version 1 updates. But we configured router 1 to only accept version 2. So if we go up to router 1 and run a debug, I think we're going to see a problem. But what will it look like? That's what we need to know. And we can already see some ignoring going on there. We'll turn the debug off while we take a look at this. We already see some ignoring going on. It ignored a routing update packet from router 3 because it's an illegal version. It's a version 1 update, and router 1's only accepting version 2. So when you see illegal version, that means you've got a version mismatch. And that's why router 2's not seeing router 3's loopback anymore. So we've got to get everybody on the same page here. What we're going to do is go down to 2, and under RIP, I'm going to hard code it for version 2. Turn off auto summarization. Save that. We may have to go back around and clear the routing tables, because as I've mentioned before, even in a situation like this with 3 routers in a pod by themselves, distance vector protocols can actually take some time to catch up, to converge. Doesn't have 2s yet, but it will. We should have cleared. Let's clear the IP routing table again. Let's do a show again. There we go. And you see now, it looks like actually router 3's loopback has a 24-bit mask instead of 32. That's not any big deal. But you see now that the VLSM information is being carried because we're running version 2. We've got connectivity again. So we've got to watch those versions, and again, you've got to know your debugs. And you've got to know how to read what those debugs are telling us. So we've already used debug IPRP twice here in a very simple situation. So that's how we do it overall for version 2. We saw the updates. We saw how to handle it. We know now that illegal version is indicating that there's a version mismatch in there somewhere. But I want to show you one other way we could have handled that. And we're going to go to router 3 and we're going to hard code it for version 1. So router 3 now, hard coded for version 1. You see on the 3 interfaces that fall into the 2 networks that we're advertising that they're sending and receiving on 1. Let's go ahead and open up those Ethernet interfaces on routers 2 and 3. We'll do a no shut here or let them catch up. Let's try it as 2 words. There we go. While that's catching up, we'll go ahead and add the graphic here for the Ethernet segment. Just as a quick reminder, our serial network is 172.12.123.0. And our Ethernet segment is 172.12.23.0. So we're going to see some equal cost load sharing action here very shortly. Let's go to 2. And we'll ping the other side of the connection. And when you first open, you see that one packet timed out there and the rest went through. Don't worry about that. When you first open interfaces like that, you may lose the first packet during the ARP process. Or if you ping too soon, you may actually lose more than that at first while the switch does its work. And there we go. So we've got connectivity between the 2 Ethernet interfaces. And we were already advertising that in RIP. So let's see, 172.12. Let's clear that table. And we'll see the other route here in just a second. So we're now seeing an extra network, and that's what we want to see. We're going to go down to router 2 right now, though. And what we're going to do is change the version at the interface level, because RIP gives us 2 options. RIP allows us to hard code the version for the entire router, which we've done here with version 2, but we could also do it on the interface level with both sending and receiving. So right now, we've got a mismatch as we revisit router 3. We've got a mismatch because router 3 is only sending version 1, and router 1 is only accepting version 2. So that's why router 1 is not accepting routes from router 3 right now. So let's take a look at that. You can see that it's still showing as a gate, as an information source, 123.3, but the last time it got an update was 3.5 minutes ago. But the routes are still showing up because of slow convergence. So what we're going to do right now then is go down to 3, but use the interface level command to fix this problem. Pardon me, and just show it in action. If we go to serial 0, we can override the default that we set of version 1 with the IGRP send command. And we're going to send version 2 updates. And we're going to receive version 2 updates, but only on this particular interface. If we run show IP protocols at this point, you'll see the change here, that the default right now is send version 1, receive version 1, because we put the version 1 command under the RIP process. But now on serial 0, it's sending and receiving version 2, because the commands that we put in here are overriding the default. So now we know how to set this version at the protocol level and how to set it at the interface level. And if we go to router 1 now, let's see what we get. Now we're seeing equal cost load balancing to that Ethernet segment, because it's now accepting routes from router 3 again. So that's how we change it at the interface level. Let's take a quick look then at router 2. Always running show IP protocols. Again, router 2 is hard-coded to send version 2 updates. Router 3 on the Ethernet interface is still sending version 1. So we're going to change that at the interface level too, just for the practice. IGRP send version 2. And it's legal, you can put both versions on the interface command as well. So right now we're sending version 2 but accepting version 1 and 2 on the Ethernet 0 interface. There is no overriding reason that we're doing that here except to illustrate the usage of the commands. And you see now that we've configured the Ethernet interface to send version 2 and receive versions 1 and 2. So just think that can come in handy on occasion in production networks as well. Generally, you are just going to use version 2 and hard-code it, or version 1, hard-code it for that. But in case you need to do it on the interface level, now you can do so. So what we're going to do now is tackle authentication. And we're going to configure both kinds of authentication, both clear text and MD5, so you can see what they look like. I'll put this over in red so it's a little more visible with what we're adding here. We are going to add MD5 authentication to our frame. Because hey, our frame is important. We don't want anybody tapping into that. So we're going to change that to MD5 authentication. We're going to go to router 1 and put it on there first. And first we've got to create that keychain. And we're just going to call the keychain, we're just going to call it RIP. Now we have to create a key number, which we'll call 1, and set a password. And this is the actual password that's going to get passed around, no pun intended. So now I have created the keychain. Let's try show keychain instead. Does that work? Yep. If you want to see the keychains that you've configured on a router so far, it's show keychain but without the hyphen in it, no dash. And it's going to show you immediately what the password is. And these accept and send lifetimes, you'll get into this during your security studies. It's not something we're going to do here today. But you can write keychains that are only valid at certain times of the day. So we've written the keychain, Now we've got to apply it, and that is applied at the interface level. So we'll just call it interface serial 0. First we have to name the protocol, authentication, and then the mode. And you recall from our discussion earlier that our two choices here are MD5, which is a hash, and text, which means clear text authentication. So we're going to configure MD5 there, but we're not done. Now we've got to name the keychain. A lot of typing here, huh? I could have used my up arrow and backed over some of that if I wanted to. So now at this point we have authentication configured on router 1, but not the other two. So if we clear our routing table again, what will we get here for RIP routes? What will we have when I hit this button? Nothing. Let's find out why with debug IP RIP. We'll clear the routing table again to force the updates. Let's see what we get here. Well, we sent the request 224.0.0.9, and that's what we expected because everybody's sending and receiving version 2 right now at least. So we see 224.0.0.9, but right off the bat we see right there at the bottom that we ignored a version 2 packet from 172.12, 123.3, and now .2, and I'll kill the debug here. And there, just another one just came in. Invalid authentication. And you thought this was a simple debug. This is the third different kind of message we've seen about why we're not getting a packet. The reason that we see invalid authentication, either the password is wrong or authentication is not configured on the other side of the link. It's one of the two. So what we're going to do right now is go down to router 2 and configure authentication just the same way we just did it. We're going to create the keychain first. Same password. We can go straight to the interface from here too. You don't always have to go all the way back out. You can see how the prompt changed to the interface configuration command. Level, I should say. Interface serial 0, IP RIP authentication. Mode, MD5. IP RIP authentication. Keychain RIP. We'll do a WR there, go back up to router 1. See if we see any routes yet. Yeah, we're getting some RIP routes, and notice that the next hop for both of these is 172.12.123.2. So the authentication now between router 1 and router 2 is working, but we still don't have it configured on router 3. So we'll do the same thing here. IP RIP authentication. Once you type this a couple times, you'll have it down. And then IP RIP authentication. Keychain RIP. Make sure you put the name of the keychain there and not the key string. It's a common error. And we'll do a WR while we go back up to router 1. Show IP route RIP. Let's see. Yeah, we already see a couple of changes here, so we know authentication is working. The next hop for the network 3 is now 123.3, and we also see that equal cost load sharing is in effect. So that it's just that simple. Now the passwords, the updates are authenticated. Let's run debug IP RIP and see what we can see there. IP route. And let's take a look at some of these. And you can see the building flash entries. It's ignoring a loopback. That's normal. A packet from its own loopback. Let's go ahead and turn off the debug here. And you'll notice that you see the message received packet with MD5 authentication. So it's actually telling you that this packet is being authenticated. It's being authenticated with MD5. But you'll notice you don't see the password anywhere, which is good. That's the reason we're running it. Now what we're going to do is configure clear text authentication over the Ethernet link between router 2 and router 3. So we're going to build some more keychains, but we're going to use clear text authentication to see what the issue is, to see what we see, I should say, with the debug. So let's go down to 2, conf t, we're going to call it RIP2, key 1, we'll use CCNP, since everybody here is going to be a CCNP shortly. We'll use that for a key string on interface Ethernet 0, same commands, mode text though, and then IP RIP authentication, keychain RIP2. We'll go over to 3, do the exact same thing, call it keychain RIP2, key 1, key string, CCNP, interface Ethernet 0, IP RIP authentication, mode text, IP RIP authentication, keychain RIP2. We're all set. So let's clear the routing table. We're going to run a debug right here so we can watch the packet come in from the Ethernet interface. Let's see if we see anything unusual here. Let's run undebug all. And that's part of being a skilled network administrator, is being able to look at all this and find out what the problem is. Pretty obvious here though. Note that the packet was received with text authentication, and it actually shows you what the password is. So it's just this easy to see what the password is when you're using clear text authentication. It says invalid authentication, but we know that we've got authentication set up. We know that we've got text authentication set up, so what's the problem? What is the problem? Here are our 2 keychains on router 3. Here are our 2 keychains on router 2. What's the problem? It's right in front of you. You might even have caught it when I did it. The answer, I'll give you that much of a hint, it's right in front of you. It's a case sensitivity issue. On router 3, I configured CCNP in lowercase, and on router 2, I put it in uppercase. That is the problem. The router's not going to point that out to you. This debug is good, but it's not that good. It's just going to give you a message that there's invalid authentication. And the second you see that, check your cases. Uppercase versus lowercase. We're going to go over to 3 now. Let's do those keychains again. I'm just going to delete the keychain RIP2 and then write it again. And again, it's just no keychain RIP2. I'm going to put it right back, and with a key string of CCNP in uppercase. I do not have to apply it to the interface again. That's the theory. Let's test it out. Let's run a debug IP RIP and then clear our routing table and see if we get the packet from the Ethernet interface that we expect to see. And I already saw it come in. There it is again. We'll quickly do an undebug all. We go up and see that we received a packet with text authentication CCNP, and this time it was accepted. There are the contents of the packet. And you can see that the next hop to reach the loopback is through the Ethernet segment. Let's try that again. There we go. Through the Ethernet segment right there. The next hop is 23.2 to reach router 2's loopback. So that's how we debug. Boy, we debugged a lot there. I mean, we saw split horizon in action. We saw a couple of common authentication issues. And again, the command's a little tricky when you first start with it, but it's really not that bad. But it's commonly misconfigured because people will, first off, do it on one side of the link and not the other. And they'll also use the wrong text on one side. They'll have the password in incorrectly. Also, keep in mind that both sides of the link have to agree on the kind of authentication being used. If we had configured routers 2 and 3 there with the same password, but one side is using MD5 and the other side is using text, then it's not going to work out. There's really no extra work on the router. There's very little extra load to use MD5 authentication. So in your home lab, in your rack rental studies, and your BSCI studies, I urge you to know how to configure both kinds and how to troubleshoot both kinds. But in the real world, in a production network, go ahead and use MD5 authentication. Because as you saw with our little debug here, anybody who knows how to run a debug for RIP can see your passwords if you put them in clear text. And that's not what we want.